All right, so these are your notes for section 1 of chapter 10. Chapter 10 is over states of matter. This first section is about the kinetic molecular theory of matter. All right, so your objectives are to state the kinetic molecular theory of matter and describe how it explains certain properties of matter. And then we're going to talk about the 5 assumptions of the chem theory, define ideal and real gases. We're going to describe each of the following characteristic properties of gases: expansion, density, fluidity, compressibility, diffusion, and diffusion. And then finally, we're going to describe the conditions under which a real gas deviates from an ideal gas. All right, so let's jump into this. Kinetic molecular theory. It's an idea that particles of matter are always in motion. So we've talked about that before, how it doesn't matter if it's a solid, liquid, or a gas. Even though a solid looks like it's not moving, right? Your pencil laying on your desk doesn't look like it's moving. Particles within that solid are still moving, right? They might just be vibrating around fixed positions, but there's still movement. Right, so this theory explains the properties of matter in terms of energy and forces. So we're going to talk about how fast those particles are moving, and we're going to talk about how those particles are attracted to each other. An ideal gas is a hypothetical gas that perfectly fits all assumptions of the chem theory. Right? So in an ideal world, all gases would behave this way, but they don't really. That's why we have ideal gas and actual gas later on that we'll talk about. Right? But there are certain assumptions that we have with this kinetic molecular theory, and we need to go through those. Your first assumption is that gases consist of large numbers of tiny particles that are really far apart from each other relative to their size. So that means that a gas is mostly empty space, and that explains a lot of things about a gas. We know that gases have extremely low densities. We know that gases are compressible. We've demonstrated that before. We demonstrated it again with the syringe. Right? You can compress a gas fairly easily. And the reason for that is because there's lots of space in between those particles. And all that space, all that empty space, means that there's a really low mass compared to the volume, which gives you a low density. Assumption number 2. Right, you have collisions between gas particles, between particles and container walls, and those are going to be elastic. Those collisions are elastic. And with elastic collisions, that means that there's no net loss in total kinetic energy. So these particles are flying around really, really fast, and when they bounce off of something, they don't speed up, they don't slow down, they keep the same amount of energy constantly. Right? So there's no net loss in total kinetic energy. That energy is transferred in some cases, but there should be no net loss at constant temperature. So when two particles collide, one might go faster than the other after the fact, but there's no net loss. It's still elastic. Right, so again, assumption 1, tiny particles really far apart. So gases have that low density that's characteristic to them. They're compressible. Collisions are elastic, so there's no net loss in that total kinetic energy. So that means that at least at a constant temperature, right, the relative amount of energy in a sample of a gas is going to be the same. Right, temperature is a measure of kinetic energy, so as long as it's a constant temperature, obviously the kinetic energy is going to be the same. Assumption number 3, gas particles are in continuous rapid random motion, therefore possessing kinetic energy. Kinetic energy, again, is just moving energy as opposed to potential energy that's stored. The big thing for a gas is that the energy of the motion is bigger than the attractive forces between particles, which is why a gas is a gas as opposed to a solid or a liquid. Solids and liquids, the attraction between particles is big enough that they stay together. Whereas in a gas, that kinetic energy is so big that, and the attraction relatively so small, that they're actually going to be a gas to begin with. They're not really going to, those particles really don't interact with each other at that point because they're moving too quickly and they're too fast, they're too far apart. So something becomes a gas once that kinetic energy becomes so big relative to that attraction between particles. That's what causes a gas to be a gas to begin with. Assumption 4, no forces of attraction between gas particles. Obviously there would be some attraction, it's just so small compared to the kinetic energy that it's negligible, it's not noticeable. So again, this is an ideal condition here. We're just assuming that there are absolutely no forces. That's not always true, but for an ideal gas it's true. And then number 5, the temperature of a gas depends on the average kinetic energy, because kinetic energy is a measure of temperature, so they are basically the same thing. So one depends on the other because one is a measure of the other. Again, we're going to assume that there are no forces of attraction between particles. And number 3, you got that continuous, rapid, random motion. Right? That energy is so big that it overcomes that attraction. There's relatively little attraction, so small of an attraction in a sense that it's negligible. Excuse me. And then the temperature and kinetic energy is essentially the same thing. So those are our assumptions. Quick rundown one more time. I got lots of tiny particles that are really far apart. Gives you a low density, you can compress it. 2, collisions are elastic, so there's no net loss as they bounce off of each other at a constant temperature. They're the same amount of total kinetic energy. 3, those particles are continuously rapidly moving in random directions. At a certain point, that kinetic energy gets bigger than the attraction. That's what makes a gas to begin with, but assuming it's an ideal gas, there are no forces of attraction between those gas particles. And then finally, the temperature, kinetic energy, basically the same thing. So temperature equals kinetic energy. Kinetic energy is a measurement of that temperature. So speaking of kinetic energy, there's an actual equation for kinetic energy that you guys need to know so that you can relate certain things. Kinetic energy is equal to 1/2 of a mass times the velocity of that particle squared. Right, so mass and velocity, that little v is velocity as opposed to a big V that would be a volume. But since those things multiply to make your kinetic energy, there's a relationship between mass and volume and kinetic energy. Right, so this first note here, temperature is a measurement of kinetic energy, so kinetic energy should be proportional, that's what that alpha symbol means in this case, to temperature. So as that temperature increases, so does that kinetic energy. But assuming that that kinetic energy, that temperature is constant, as a mass increases, the volume would have to decrease in order for that kinetic energy, in order for that temperature to remain constant. So those two things are actually inversely proportional. So if you have a heavier gas particle versus a lighter gas particle, and they're both at the same temperature, that means the heavier one has to be moving slower than the lighter one, otherwise they wouldn't have the same amount of energy. So it's a relationship that we're going to have to understand and use to understand a couple different things later, diffusion and fusion. But that mass and that velocity, they're inversely proportional, right? If it has a bigger mass, it doesn't have to be moving as quickly to have a huge amount of energy. It's a momentum thing. Okay, our physical properties of a gas. Right, some different things that we're supposed to be able to explain. You have expansion, right? So you have assumptions 3 and 4 kind of working together for that, right? Number 3 says that gases move continuously, rapidly in random directions. So therefore, they actually would tend to spread out as opposed to shrink into a smaller volume, right? So gases expand to fill the volume of their container because the particles move randomly, rapidly, continuously until they reach the farthest corners of that container, right? And number 4, there's no net forces of attraction. Attraction would also keep gases in a smaller volume, right? So gases will expand. They expand in order to fill that container, right? Because particles move randomly and rapidly, continuously, and they're not attracted to each other, so they tend to spread out, right? Fluidity, another property of gases, right? Fluids are gases and liquids in science terms. I know that normally you think of a fluid as being a liquid because you talk about fluids that way in other contexts. But fluidity just means that they are allowed to move. The particles are allowed to move. So again, number 4, since there's no attraction between particles, they can move wherever the heck they want to go, right? Those particles are randomly, rapidly moving and continuously in different directions, right? They're definitely allowed to flow. And that's the definition of fluidity, is that they're moving around and they're not attracted to each other. Right? That relative attraction is really, really small. So that's based off of assumption 4, a little bit of assumption 3 as well. But that's fluidity. We also have that low density that's characteristic of gases. Again, the big thing there is there's so much empty space that mass compared to the volume is really, really low. Since it's mostly empty space, there's a really small mass that's contained in a relatively large volume, and that's what density is, mass divided by volume. So you're going to have a small density for a gas. Compressibility, again, right back to assumption 1, since there's lots of empty space, in theory you could push those particles closer together, which is why you can compress a gas. So the particles are really far apart, which is why you can make them to get closer together, which is compressibility in a nutshell. Right? So you can push those particles that are really, really far apart closer together. And there's also these diffusion and effusion definitions that we have to deal with. Right? Gases diffuse and they also effuse. They're different things. You just have to understand which definition's which. Diffusion, though, is something we've talked about before, how things spontaneously mix. So considering in assumption number 3, right, gases, the particles are moving rapidly, continuously, randomly, right? Spontaneously, if you release different gases in the same container, they're going to mix until there's an even distribution of those gases throughout that container. Right? So they're spontaneously going to mix because they move randomly. Right? Particles of one gas are going to move away from each other, and so is the other gas, until the particles are as far apart as possible, but they're going to be mixed together at the end at the same time. Effusion is the process by which particles pass through a small opening. So if you had 2 separate containers containing gases, and there's a small tube connecting those 2 things, right, some gases will pass through that opening more quickly, more efficiently than others, right? And that is dependent on a few different things. Effusion is proportional to that velocity of that gas, how fast that gas is moving. So as that velocity increases, that diffusion rate increases, because they're directly proportional. But as that velocity increases, that means that it had to have had a smaller mass with the same temperature. If you remember from before, mass and velocity are actually inversely proportional. So if you have a high diffusion rate, a lot of times that would mean that you have a small mass and a big velocity, as long as you're talking about things of the same temperature. The one that diffuses the fastest is the one that has the smallest mass. Right, but another way that you can increase that diffusion rate is by increasing the temperature, because the temperature is proportional to the velocity of the particle, which is proportional to the diffusion. So as you increase the temperature, which is just that measurement of kinetic energy, as you increase the amount of energy of those particles, they diffuse more rapidly. So again, diffusion is just about spontaneous mixing of particles. Again, you go right to assumption 3 because it talks about random, rapid, continuous movement. Diffusion, you need those particles to pass through a small opening, and that depends on the kinetic energy, the temperature, just like the diffusion actually depends on kinetic energy, temperature. Right? Gases diffuse more quickly and more efficiently with a higher temperature. But diffusion rates, generally speaking, right, they're going to increase as the velocity of the particle increases. So different ways that you can increase the rate of diffusion is either by increasing the temperature, or you could have the same temperature with a smaller mass. Right? Those particles with the smaller mass would be moving more rapidly, so that diffusion rate increases. Okay, and then most of these notes we were talking about ideal conditions, ideal gases. Real gases don't actually completely align with the assumptions of the chem theory, right? And there are certain scenarios in which gases really don't align with those assumptions very well, so those are the conditions that we're worried about, right? Gases that are at either high pressures or low temperatures tend to deviate, because at that point, at a high pressure or low temperature, it's harder for that kinetic energy to overcome those intermolecular forces. And once those particles are more attracted to each other, right, once that attraction gets bigger than their ability to move away from each other, that's when a gas becomes a liquid or a solid, remember. The other situations in which gases tend to deviate from those ideal conditions, right? Very polar gases, the more polar a gas, the more likely it is that they're going to deviate. So if I compare two gases, right, maybe methane and water, right, those particles, those molecules are basically the same size. They have a really similar mass. But one of those things is a gas at room temperature, the other thing's a liquid. And the reason for that, methane being a gas at room temperature versus the water being a liquid, is that water has a lot of attraction. Right? You know that water molecules tend to make those polar interactions. Right? There are hydrogen bonds between one water molecule and another. That huge amount of attraction is what prevents that water from being a gas at room temperature. Right? You can heat that water to a high enough temperature that then that movement, the energy of those particles, overcomes the attraction between those particles, and it will become a gas. But at room temperature, it's a liquid, versus methane that's a gas at room temperature, because there's relatively little attraction between the nonpolar molecules of that methane versus the polar molecules of water, right? There's a lot more attraction there. So polarity can influence right? Those conditions that we talked about before, right? The more polar it is, the more likely it is to deviate from those ideal conditions, from those assumptions that we talked about. So this last question here, whiteboard question, what would eventually happen to a gas if you continue to increase the pressure and or lower the temperature? Remember, there's a reason why they tend to deviate at high pressures and low temperatures. You know that if I take that gas, right, maybe I talked about gaseous water vapor. As I decrease the temperature of that, eventually it's going to turn right into a liquid, right? And I can also put enough pressure on a gas that eventually those particles are close together and they become a liquid, right? Because the attractions can then take over. So that's the basic idea here. No need to worry about this as a whiteboard question later. Just understand that the reason why high pressure, low temperatures, why those things deviate is because they're actually more likely to be a liquid than a gas at that point. Right? Because that's when those attractions take over. And then also, if that particle happens to be polar versus nonpolar, there tends to be more attraction. That also makes a gas deviate from those ideal conditions. All right, so that's it for this section.